The recording restarted. I would like repeatedly to invite Paweł Gora, University of Warsaw in Poland.
Okay. Hello,
Paweł.
everyone. Thank you.
Yeah.
Thank you for the invitation. Can you see my screen now?
Now, yes. Now it's in the full screen mode.
Great. Great. Thank you. Okay, fantastic. So let me start and let me introduce myself. So my name is Paweł Gora, as introduced. I'm a PhD candidate at the University of Warsaw, Faculty of Mathematics and Computer Science. At the same time, I'm also the founder and CEO of the Quantum AI Foundation. So we are a charity organization aiming to support research, education, and collaboration in new technologies, especially quantum computing. I'm also a board member of Qword. So yesterday there was a presentation about Qword given by Abuzaria Karilmas. Qword is also an international initiative aiming to build an open global quantum computing ecosystem. And I also coordinate the local chapter, local QCousin of Qword here in Poland. But today I will give a talk about solving vehicle routing problems using quantum computing. So this research, or the research that I will present, was carried out at the University of Warsaw about 2 years ago. But now it's, this research is still going on, in fact. But now it's also part of the Q research program within Qword. So let's start from some basic definitions of the traveling salesman problem and vehicle routing problem, because I believe that for some people from the audience, this may be some new concepts. The traveling salesman problem and vehicle routing problem are quite popular problems in computer science. So we have a directed graph with non-negative costs assigned to edges. And in the traveling salesman problem, TSP, that is also called TSP, we have n selected vertices in the graph. So we can think about them as our customers that we would like to visit to deliver some products, for example. And now the question is, what is the shortest or the least expensive possible route that visits all of them and returns to the original vertex, to our depot? In the vehicle routing problem, we also have n selected vertices in the graph, but then we ask what's the optimal set of up to m routes, which in total visit all the selected vertices and start and end in the depot. And each vertex, in both cases, each vertex should be visited only once beside the depot. So in this case, we may have up to m vehicles, but in the original definition, we can just assume that there is only one vehicle, but this vehicle can just return to the depot to just take some new products. There are also some variants, even more interesting, more practical variants with some additional constraints like capacitated vehicle routing problems. So here we assume that the capacities of vehicles are bounded. We may also introduce time windows in which some locations should be visited. And all these problems are NP-hard. So it means that most likely there are no polynomial time algorithms able to find the optimal, the exact solutions for these problems. Okay, so how we can solve these problems using quantum computing? So there might be several approaches and several ways how quantum computing can help. So today in this talk, I will focus on the quantum annealing approach, but at the end, I will also sketch what might be some other approaches, what might be some other ways of using quantum computing to solve or to tackle these problems. So I believe that at least some of you, or most, or maybe even all of you, heard about quantum annealing. So first, in quantum annealing, we first define the ground state. We first define the initial Hamiltonian for which the ground state is easy to prepare. And we also have to prepare the final Hamiltonian that should correspond to our optimization problem, so that the ground state is also the solution of our optimization problem. So this Hamiltonian corresponding to the Ising model should be also defined as something that's called QUBO, the quantum unconstrained binary optimization problem. So in QUBO, in quantum unconstrained binary optimization, we have binary variables that may take values 0 or 1. We also have some parameters, and the goal is to find the minimum or maximum value of this function, of this QUBO. And this QUBO formulation corresponds to the Ising model from the ferromagnetism. That's why we can also try to solve this kind of problems using quantum annealing by modifying the strength of the magnetic field. We can slowly modify our initial Hamiltonian to the state of the final Hamiltonian, and hopefully, if we do it slow enough, and if we do it in an adiabatic way, there are chances that we'll find good solution for this problem. So in theory, if this is an adiabatic process and we do it slow enough, then it should be the global minimum. But in practice, we should rather expect that it will be heuristically optimal solution. So relatively close to the optimal solution, but not necessarily the optimal one. Okay, so how we can now define the vehicle routing problem in the terms of such a QUBO formulation. So the important thing is to know that the formulation, the QUBO formulation that I will present, is not the only possible QUBO formulation for this problem. So I am aware of at least a few possible QUBO formulations, and the research on QUBO formulations for this problem is still ongoing as well. But I will present the QUBO formulation that we discovered, that we designed here at the University of Warsaw. So we have a set of identifiers that may correspond to our trucks, our vehicles, and we also have a set of up to n or n+1 locations, vertices in our graph. So the identifiers from 1 to n correspond to our customers, n+1 is our depot. We also have costs assigned, cost of travel from node I to node J assigned to our edges in the graph. So we also assume that the cost of staying in the same location is 0. And finally, we introduce our binary variables, x, I, j, k. So we assume that the value of this such binary variable is equal to 1 if and only if in a given setting, in a given solution, the vehicle I visits the node J as the kth location on its route, and otherwise the value should be 0. So here are some observations that could be used to just reduce the complexity of the problem and assign some specific values to certain variables. So for each vehicle I, x, I, n+1, 0 should be equal to 1, which means that the depot should be also the first location on the route for each vehicle, right? So we always start from the depot, and also for other j's, for j's lower than n+1, so for locations different than the depot, the value for k equal to 0 should be also equal to 0. And also, if the value of the variable for the depot, for visiting depot, is equal to 1, then for all higher indices, the value of the corresponding variable should be equal to 0. So we assume that if a given vehicle returns to the depot, then it should stay in the depot. This is the problem Hamiltonian. This is the QUBO formulation, in fact. So it may look complicated, but I will try to give you an intuition how to think about it. So as you can see, we have 3 components here. So the first component is a sum of all costs of travels from the depot to the first visited node. So that's the first section of each car's route. So we have just a sum over all vehicles or cars. And here we consider the costs of traveling from the depot to one location, another location, that should be the first location on the route of the vehicle M, right? So this component should correspond to the cost of traveling the first to the first locations for each vehicle. The second component is a cost of the last section of a route, so traveling to the depot, in a special case when a single car serves all N orders on N locations. And only in such a case, this component can be greater than 0. For all other cases or other solutions, this component will be just equal to 0. And finally, the last part is the cost of all other sections of routes. So that's our cost Hamiltonian. That's our QBO that we would like to minimize, in fact, but with some constraints, because if we have binary variables, then we can easily see that the minimum of this function is achieved when the values of all binary variables are just equal to 0. But it's not an interesting solution for us, right? Because we don't have any travels. So we would like to travel and we would like to visit some locations. So that's why we also have to introduce some additional constraints. So in order to consider these constraints, let's consider a binary function. So this is a binary function with an interesting property that the minimum value is equal to -1 here. And this value can be achieved only if exactly one of these binary variables from y1 to yn is equal to 1. So only in this case, we achieve the minimum. And now we can also formulate another quadratic function of binary variables composed of these functions a for different variables for our binary variables x. And here, the first component or minimizing the first component corresponds to assuring that each delivery is served by exactly one vehicle and exactly once. Because in such a case, each location, so each location k, if this location is visited only once and by only one vehicle, then we achieve the minimum value of this function a. And if we have it for all locations, then we can be sure that each delivery is served by exactly one vehicle and exactly once. And minimizing the second component corresponds to assuring that each vehicle is in exactly one place and at a given time, right? So here in this function as arguments, we consider all possible locations, right? But all possible vehicles and orders, but we assume that each vehicle in each step can be in only one location. Okay, and finally, this is the final, the total Hamiltonian. So here we have our cost Hamiltonian that we would like to minimize, and here we have then the QBO corresponding to our constraints. So this is something that we would like to minimize at the same time. So in fact, we want to minimize both functions, and in order to be sure that we minimize C, but by assuming or ensuring that the value of Q is the global minimum, we should set the values of parameters A1 and A2 to such values that A2 should be much larger than A1, basically, right? So in our experiments, it turned out that it should be a few orders of magnitude larger than A1. And then we'll be sure that Q achieves, so when we apply a solver like quantum annealer, we'll be sure that we achieve a global minimum of Q so that our constraints are satisfied. But at the same time, we should be also able to find relatively good solution for our problem Hamiltonian C. Okay, so we can just apply standard solvers from D-Wave's quantum annealing library, LEAP. So D-Wave is the company from Canada working on quantum annealers, and we use their machines to run these experiments. As you can imagine, the quality, the efficiency of this approach may also depend on the number of binary variables because they correspond to the qubits, right? So in order to decrease the number of required qubits and the number of binary variables, we can assume that for each vehicle serves approximately the same number of orders. Let's say up to A plus L deliveries, where A is the total sum of orders divided by the number of vehicles. And L is a parameter called limit radius, which controls the number of orders. So it's reasonable because in practice, we usually want our fleet to be evenly loaded, right? So this assumption help us reduce the number of required qubits and binary variables. We can also think about some other approaches. So this is the DB-scan solver, in which this is a hybrid solver in which we combine a quantum approach with a classical algorithm that is recursive DB-scan. In recursive DB-scan, we first cluster all the nodes, all the locations in the graph, and then we assume that each cluster is served by exactly one vehicle. So for each cluster, we solve an instance of the traveling salesman problem. So this is an example of an approach that is called cluster first, solve or solution second. So first we cluster our nodes, and then for each node, we try to solve the instance of the traveling salesman problem. We can also do the opposite. So we can first try to solve an instance of the traveling salesman problem. So the problem with one vehicle for all nodes in our graph, all locations in our graph. And then we can try to divide this solution into many solutions and assume that each component should be traveled by one vehicle, right? So for this, we can perform a dynamic programming, right? So we can define a partial solution, a solution for orders from D1 to DI and for a given set of vehicles S. And then if we compute these values for smaller instances with lower number of orders and smaller set of vehicles, then we can construct the solutions for larger instances. We can also even this approach by assuming that instead of considering a set of vehicles, we may consider a sequence of vehicles. Okay, so these were just four approaches to solve these problems, and now I'll present the results of experiments. So basically our goal was to compare results of different algorithms, both quantum and classical, and also hybrid algorithms on several data sets. For quantum and hybrid algorithms, we ran experiments using D-Wave platform. So as I said, D-Wave is a company working on quantum annealing. We tested two solvers, QBsolve that's a quantum solver, and we ran experiments on both quantum processing unit and on CPU. So in this case, it was just a simulator of the quantum annealer. And we also ran experiments on a hybrid solver that utilized QPU and CPU at the same time. And in case of classical algorithms, we tested simulated annealing, B algorithm, evolutionary annealing, and DB-scan with simulated annealing. So these are some interesting, important, and popular heuristics, meta-heuristics that are available in the scientific literature, aiming to solve the vehicle routing problem. We also prepared several data sets. So the first data set was Christofides 1979. So this is a standard benchmark data set for the capacity vehicle routing problem. It's well known and frequently studied by the scientific community. And there were 14 tests with different number of vehicles, different capacities, and different number of orders. But we also built a data set based on a realistic road network of Belgium acquired from the OpenStreetMap service. So later I will tell why we selected the road network of Belgium and not of Poland, for example. So this is the structure of this Christofides data set. So we selected several instances with different number of vehicles, different capacities, different number of orders. And in our data set built based on the OpenStreetMap service, there were also different number of orders and different locations of orders. So there were relatively small data sets with just a few orders, but there were also larger data sets with even 200 locations. So these are the results of experiments. So it turned out that Even for relatively small instances with, let's say, 1, 2, or 3 vehicles, very fast. So very soon we are not able to solve these instances using just a standard quantum processing unit and using this basic solver that is full Cubo solver. So the first solver that I presented. So the quantum annealer was not able to find good solutions or any solutions, in fact. It was a bit better in case of simulators and running experiments on CPU. It was also better in case of the hybrid approach. Later we ran experiments for larger instances, and it turned out that, again, there are issues for this full Cubo solver, even for running experiments on CPU or using the hybrid solver. It was better in case of this average partitioning solver where we reduce the number of binary variables. So then we are able to solve larger instances. For bigger instances, we also compared this average partitioning solver with DB scan solver. It turned out that DBSS can achieve better results in most cases. So in later experiments, we used the DB scan solver and compare it with a solution partitioning solver. So with this last approach that I presented. And again, solution partitioning solver turned out to be better. So we decided to compare it with classical algorithms. And when we run experiments on our data sets, it turns out that these classical algorithms are still better in most cases, but in some cases the results are comparable at least. But when you run experiments on the Christofides data set, so the standard benchmark data set, it turned out that for many instances, this solution partitioning solver run using hybrid solver from DOA was able to find better or at least comparable results to classical solvers. So just some conclusions. It doesn't make sense, or at least it didn't make sense, to run experiments just on standard quantum processing unit for large test cases. I said it didn't make sense because we ran experiments on the previous version of the quantum annealer available in the LEAP framework. Now D-Wave has more powerful quantum annealer, so we are also going to repeat these experiments for the newest machine from D-Wave. The solution partitioning solver gives the best results among quantum algorithms. We compare it with classical meta-heuristics, and it usually gives a bit worse, but sometimes better. So at least comparable results. Here is a GitHub repository. So the code used for experiments is open source. You can freely use it if you want. It's available in the D-Wave examples repository. So we're invited by D-Wave to just publish our code there. And if you are interested in the further details, this work was also published in the article, New Hybrid Quantum Annealing Algorithms for Solving Vehicle Routing Problem, and it was presented in 2020 at the ICCS conference. And here are the contributors from the University of Warsaw. This research was carried out within the EIT Food project funded by the European Union. So EIT Food is an initiative aiming to support innovations in the food sector. A Colorado group from Belgium was one of our partners, and that's the reason why the experiments were carried out on the road network of Belgium, close to Brussels. And I can also tell you that this research is ongoing. So now we are also investigating some other approaches like quantum local searches, higher order binary optimization, QAOA, VQE, surrogate optimization to find good values for these relaxation parameters that stay close to the constraints or next to the constraints. We also investigate quantum neural networks, so some kind of quantum enhanced machine learning approach for this. There might be also other Cubo formulations. As I said, we also want to scale this approach. So we are investigating some graph clustering, graph coarsening approaches to just reduce the complexity of the instances and first solve the smaller instances and build larger solutions in a classical way. We consider some additional constraints and investigate for which scenario the hybrid algorithms can give the best results comparing to classical algorithms. And that's it. Hopefully the results of this research will be presented and published in a book and in a series of popular science articles. I hope you enjoyed. I thank you for your attention. And if you have any questions, I'll be happy to answer.
Yes, Pavel, thank you. We did enjoy it. You solve very interesting and important problems. We have time for one quick question, if any? Well, if it is not the case, this gives us only a few minutes of an extremely short coffee break. Thanks again, Pavel.
Thank you.
Now